Okay, today we're going to do the rectilinear flight cruise condition. So I'm going to lecture on the screen for a bit and then maybe switch over to the camera. So this is in chapter 4. We started chapter 4 with the stability review, and now we're talking about a cruise trim condition. And we start with the steady state equations of motion. There we go. So from chapter 1, these are the steady state equations of motion. And we're going to specialize these for the cruise condition. We did this in chapter 1, but we're going to talk through it again. We set P, Q, and R to 0. And so we knock out those terms, and then we do it in the stability axis. So we knock out those terms as well. So these are the terms that we're going to be knocking out. So a lot of stuff goes away. So the equations become really simple. And then on the, sorry for the up and down, then on the right side over here, we're going to plug in our force and moment and linear models. And I've copied a page out of the book here. These are, this is FAX, FAZ, and M. And then we have the lateral directional ones as well. So we're going to stick those in the right side of the equation. Here's the lateral directional forces and moments in terms of beta, aileron, and rudder. So all of those get stuffed into the equations on the right side of this set here with the appropriate terms knocked out. So that's what I'm going to write next, or what those equations are. So that's what's left of the equation, and then we plug in the force and moment models. That's the aerodynamic, and then here's the thrust. So that's the X force equation. And then the Y force equation is going to be, have the gravity vector in the Y direction. And instead of alpha and IH and delta E, this is a lateral directional force and moment. So we have CY So that's Cy beta times beta. There's the aileron side force. There's the rudder side force. And then any thrust side force we might have. And then we have the Z force. And we have all these ones because remember this is steady state. Because that's what we're doing, a steady state flight right now. And the lift model is going to be CL0, CL alpha times alpha, CL IH. So it has the longitudinal force and moment terms. And then it has the thrust component in the vertical or lift direction. And so these are the force equations. So far, so good. And remember, this is cruise, it's trim, add stability axis to this, because that's what we're doing all our analysis in. So now I need to write the moment equations, but I'm going to give you a chance to catch up here before I scroll up. That's the incidence angle of the horizontal tail, the setting angle where it's fixed to the airplane, or it can vary if it's an all-moving tail. He asked what IH was. All right, and while we're on this page, let's identify the unknowns. In other words, what are the parameters that we're going to have to solve for? So obviously we know mass, we know gravity, we know S, the wing area, and we know all the parameters like CD alpha, CDIH, CY beta. Those are all calculated based on the geometry of the airplane. But the unknowns in here are these things, because we can fly at any angle of attack we want. We can set IH, we can set delta E, beta, we don't know. We could fly at any beta. We can put the aileron and the rudder wherever we want. And the thrust, we can set the throttle. So there's unknowns everywhere. Theta is an unknown. Bank angle is an unknown because we can fly at whatever bank angle we want. And we need to recall that in stability axis, theta 1 is the same thing as the flight path angle. Remember that we drew that picture, and because the stability axis points into the relative wind, then the pitch angle is the same as the angle, the flight path angle. All right, what color do you like? Is black good, or would you prefer to change up to a green or something? He's shaking his head. No, black shows up better. Blue? Okay, we'll try that. If you hate it, say something. Okay, so here's the pitching moment, or the moment equations now. Can you see that okay, or do you hate it? Thumbs up or thumbs down? Good? Okay, we'll try it. If you change your mind, let me know. So this is the rolling moment equation. It's just, remember that one's easy. It's just the moment, total moment is 0, because that's a trim condition. Is the pitching moment, rolling moment, and yawing moment are all 0, which means the airplane doesn't roll, pitch, or yaw. And so there's the aerodynamic part, and then the thrust part, we didn't go beyond just saying, well, there could be a rolling moment due to the thrust, depending on what happens. Here's the pitching moment equation. And there's that thrust times the moment arm that gives you the pitch. So the DT is that moment arm of the thrust line, remember, above the CG. And then here's the yawing moment. So let's circle the unknowns here as well. Of course, the thrust is in LT and NT. And I forgot to circle that inside dynamic pressure is an unknown. That's the total velocity, right? 1/2 rho v squared, because we can fly at different airspeeds. So inside here is the magnitude of the total airspeed. So let's make a list. How does that show up? Is that okay? Trying to keep you awake with all kinds of dazzling colors, right? So somebody shout out an unknown and I'm going to write it down. Did you say theta or beta? Beta. Okay, let's write that down. Okay, it's going to get harder because he's already taken one. Somebody else shout out another unknown. Alpha? Is that what you said? Alpha? Somebody else, loudly. Gosh, this isn't working because it's really hard to hear in here. Oh, IH, yeah. Do a couple more and then I'll just keep writing. Somebody else grab one. You see what we're talking about, right? All of the unknowns. I want to list them and see if we have enough equations to solve for all of these unknowns. So another one might be V sub P, right? I'm going to write that one over here. And then we got the control derivatives. Should give everybody in here your own microphone, then you all zoom in, and then it goes over the speakers over the top here. That'd be fun. Let's see, what else am I missing? Aileron, elevator, rudder, IH, alpha, beta. What'd you say? T, the thrust. Yeah. And then we got the flight path angle. Oh, and it's not on this screen, but we've got the bank angle phi, right? Because we could bank the airplane. So V sub P is proportional to Q, so we should write that as well. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many equations? 1, 2, 3, 4, 5, 6. So we all know it's algebraic, pretty much. So we know that if we have 10 unknowns and 6 equations, we got a problem, right? So that means we're going to have to specify or choose some of these so that we can solve for the rest of the unknowns. So here's what we do. Typically, we're going to set IH. Or we'll replace the elevator with IH and throw elevator away, depending on what we use for pitch control. So typically on a conventional aircraft, you set the incidence angle so that you're good in cruise, and then you vary the elevator to fly in other flight conditions. So that knocks out one. And then typically we're going to say, well, let's set the bank angle. We're going to say we're doing a 2-minute turn and the bank angle, I don't know, is 30 degrees or something like that. All right, so now we're down to 8 unknowns and 6 equations. So the reason I wrote these all over here together is that we're going to look at different combinations of choosing and setting these different variables. So one option is option A, is we're going to set thrust and the airspeed and solve for the flight path angle. So we could do that. Mathematically, we can do that, but what's the pilot doing? So he sets the throttle. You can do that. You just put the throttle in a certain position. And then the pilot will use the stick to vary the flight path to maintain that velocity. So in a sense, the pilot experimentally is solving for what flight path angle he needs to fly at in order to maintain that airspeed. Right, you set the throttle. If the airplane starts to slow down when you're flying level, then you would start diving to get some gravity going forward so that you maintain the airspeed. Or vice versa, if you're overspeeding, you can pitch the aircraft up and slow down. And pilots often will control airspeed in that way because it responds pretty quickly to elevator that way. So that's one option. So option B is to set the flight path angle and the velocity and solve for the thrust that you need. And that's more natural, isn't it? You say, okay, I want to descend in a 3-degree glide slope to land, and I want to maintain 120 knots. What throttle do I need to put to maintain that? And that's similar to what you do in your car, right? You want to go, of course, the speed limit on the turnpike at 75 exactly, right? And so you figure out how much accelerator you need to maintain that airspeed, depending upon whether you're going up or down a hill. Or if you have like most people, you set the cruise control at 75, and it does that for you. It figures out what throttle you need. So that's option B, which really doesn't need any explanation, I don't think. And then option C is we can set the throttle and just pick a flight path angle, maybe diving at 3 degrees. And then we see what airspeed we get. And that works, right? You dive at 3 degrees, you set the throttle at full, and the airplane will just keep speeding up till the drag equals the thrust, and there's your airspeed. So the pilot will use the stick to get the flight path angle, set the throttle, and then you'll see what kind of airspeed you get out of the whole thing. You can do the same kind of thing in your car. It's less easy to do in Kansas than in Missouri, but if you find a really steep hill, you can let off on the accelerator and go down the hill and see what the maximum speed is that you reach as you go down the hill. I guess you can do that on the turnpike on a really steep hill, but I don't know how fast you'll get going. Most hills in Kansas, you'll slow down. All right, so the one that we do, the solution that we go for is this one, because typically we'll want to say, I want to show that the airplane can fly at 130 knots at 0 flight path angle, or I want to show that the airplane can climb at 3 degrees at a certain airspeed. So the solution that we're going to do is that one there. All right, so what we want to do now is we're going to solve for what's left over. We're going to solve for alpha, throttle, and elevator, and these are longitudinal. And by specifying the bank angle, we can solve for these separately because the bank angle is the only thing that connects the lateral to the longitudinal equations. So if we set that, then we can solve for those independently. And then we're going to solve for beta, aileron, and rudder as a separate set of lateral directional equations. And so this is much easier. You can solve a 3x3 problem and a 3x3 problem here instead of a 6x6. All right, so the key thing we want to look at now is the longitudinal, because we're going to focus on this one first, because that's really the cruise trim problem. So I want to go back up to the equations and look at alpha, thrust, and elevator and talk about solving. And then we'll quit, and then next time we'll actually do it. No, hang on. I'm gonna scroll up. I'm just waiting for you guys to catch up. It'll take about 5 more minutes, and then I saw there was a really fancy party being set up in the lobby of this building. I think we ought to go down and crash that party. You up for that? I mean, it looked like it was a serious party with catered open bar and catered food and everything. So it must be some endowment thing. Okay, so let's go. Last thing we're going to do here is talk about, well, can we solve this? Let's see what I get with this setting. Okay, so let's look at alpha, thrust, and elevator and where they show up. So here's our equations. This doesn't look too bad. There's alpha, and it's just multiplied by a number. Let's say CM alpha is minus 0.5. We're good there, right? Alpha shows up there. Thrust shows up here. That's nice. So I can definitely solve that equation. It's linear. We've got thrust times a number, alpha times a number. The other stuff is just going to be shoved over to the right-hand side because they're just numbers. Oh, elevator. We're solving for that, but that's no problem because it's just multiplied by a number. So looks like we got 3 unknowns in this equation, but it's a linear equation. We just have ax plus by plus cz, and we can solve for x, y, and z. Okay, how about up here? Here's those unknowns. Here's alpha. No problem there. It's multiplied by a number. Here's elevator, multiplied by a number. Here's thrust, multiplied by cosine alpha. Because here we got alpha, one of the unknowns inside cosine, and that's not linear. Okay, how about this one? Here's alpha multiplied by a number, so we can solve for that. Here's elevator. Here's thrust. No problem, but sine of alpha. Not only is that nonlinear, but we've got thrust, the unknown times another unknown. So it's like x squared or xy. So what we'll talk about next time is, well, how are we going to solve these? Because really it's what's called a transcendental equation, because it's got sines and cosines, and the unknown is inside the sines and cosines. So we need to come up with a strategy to solve it, because otherwise it's a numerical iterative solution that is really hard to do. So we'll stop here and we'll continue on next time.